Okay, we're going to have a look at page 284, question 3. Part A, it says show that the unit for specific heat capacity is joules, kilogram, Kelvin. So the way that you would work this out is you would start with our formula, E equals mc delta theta. We're going to put it into terms of specific heat capacity, so C equals E divided by m delta theta. And then all we're going to do is we're going to put in the units. So energy is joules, mass it's kilograms, -1 because it's divided by. Theta, temperature, well the SI unit for temperature is Kelvin. So again, Kelvin, and it's going to be -1 because it's divided by. So that's nice and straightforward. The heater has an output, looking at the wrong question, sorry. Part B, a meteorite, the 5 kilogram meteorite. So the mass of the meteorite is 5.0 kilograms. Landing on the surface of the Earth, its initial temperature is 500 degrees Celsius. And it loses energy at a constant rate of 120 watts. So this is the same sort of question, but rather than we're gaining energy, we're basically losing energy. So the power is 120 watts. And again, just because they've given us the power, that's immediately thinking, okay, power is energy divided by time. Okay, so you're likely to have to use that formula somewhere. So the material has got a heat capacity of 600 joules per kilogram Kelvin. So we've got to estimate its temperature after 1 hour, which is the same as 3,600 seconds. Okay, so what we're going to do is we're going to work out how much energy it has lost in that time. So energy is power multiplied by the time. So it's going to be 120 multiplied by 3,600 seconds, which gives us an answer of 432,000 joules. So that's how much energy the meteorite has lost. So let's see how much temperature it has dropped in that time. So we're going to use E equals mc delta theta. We want to work out delta theta is the energy divided by the mass times the heat capacity. So it's 432,000 divided by 5 kilos mass times by the heat capacity of the meteorite's material. And that gives us a change in temperature of 144 degrees Celsius. Okay. Now, it wants us to ask the temperature after an hour. So obviously that's going to be the temperature loss. So the final temperature of the meteorite is going to be its initial temperature, 500, take away the loss, and it gives us a final temperature of 356 degrees Celsius. That's part B. Part C, we've now going on to a kettle. So from a meteorite to a kettle. So the kettle's got 450 grams of water. So the mass of water is 0.45 kilograms. And it is showing the variation of the temperature with the water with time. So the first thing we've got to do for the first part of the question is a descriptive part of the question, and it's about the shape of the graph from 0 to 180 seconds. And you can see it's worth 4 marks. So you want to be thinking of 4 things to say. So you might start with, for the first 20 seconds, the graph is level, which indicates no change in temperature. And that's because at that time, the energy is going into heating up the body of the heating element, okay, not the water at that time. After 20 seconds, the heating element's now hot and it's transferring energy to the water. You might then comment on the shape of the graph. So it's a straight line. So you need to be sort of commenting on why is it straight. So the energy is being delivered at a constant rate. And you might say because it takes the same amount of energy to heat each gram of water by 1 degree Celsius. So therefore the temperature is going to go up at a constant rate. Hence it's a straight line. Then for the final mark, you want to say it's levelling off. And that's because obviously it's reached boiling point and it's changing state. So therefore, there's no increase in kinetic energy and therefore no increase in temperature. 4 things to say. Right, so going on to part 2. The heat capacity of water is 4,200 joules per kilogram. So we're going to use the graphs. We have to use a graph because the question is telling us we have to determine the power of the heating element of the kettle. So let's have a look. So we've got energy equals mass times the heat capacity times the change in temperature. We want to get the power of the kettle. So we're going to divide the energy by time because that is power. And we can't just do that to one side of the equation, we've got to do it to both. So we can do both sides of the equation are divided by time. Now, if we look at our graph, the change in temperature divided by the change in time is equal to the gradient. So that is going to be equal to mc times the gradient. Okay, so the power is the mass times the heat capacity times the gradient of the graph. So what you would do is you determine the gradient. Now in our textbook it's not particularly clear, but in an exam paper it would be larger and easier for you to see the numbers on the scale. So I worked out the gradient to be 100 minus 15 divided by 175 minus 20. So I worked out the gradient of the graph and I got that to be 0.55. So then we just substitute that in, so 0.45 kilograms times 4,200, the heat capacity of water, times 0.55, and that gave me a power of 1,040 watts.